So we just finished working on a combined gas law problem. We're looking at these more complex gas law problems with more than just two variables. As you can see, these take up a lot of space. So I'm going to grab a new sheet of paper to do the ideal gas law problem. So we're going to assume as we solve these problems that gases behave ideally. Most of them do. You'll learn more about real gases in Chem 1A. And we want to follow kinetic molecular theory, assuming that that's going to be true. Now, with these ideal gases then that behave perfectly, with this law, you can see that we're going to relate all these variables just at one set of conditions. And that's in contrast to the two different sets of conditions that I have in the combined gas law. We're going to use the gas constant, and that gas constant is going to show up over here. R is our gas constant. R, if I looked at this another way, is the constant that PV over NT is always equal to. So no matter what the gas and the conditions, all of these numbers always are equivalent to R. The R that we're going to use most often is going to be 0.08206 liters times atmospheres divided by moles times Kelvin. So it's got 4 units in it for the pressure, the volume, the moles, and the temperature. So that constant's going to come into play in all of our ideal gas calculations. So same basic idea, go through your variables, figure out what your problem is going to look like. So portable oxygen cylinder is 2.025 liters. It's about the size of a 2-liter bottle. It's a volume. It contains gas at 29.2 degrees Celsius, so that's a temperature, and 723 torr. And let's just say you didn't have a title here that said ideal gas law. You might be thinking, okay, these are all my ones at this point. How many moles? And once I'm done writing all those down, I can see it looks very different from the combined gas law where I had 6 different pieces of data. And so the fact that I have V, T, P, and N tells me, okay, this is going to be an ideal gas law problem. I'm solving here for moles of oxygen, and that's my N here. So N is going to be equal to P times V over RT if I rearrange those variables. Before I plug this in, any units I need to fix here? If you answered yes, that's the right answer. So I'm going to add 273.15 to get this temperature to Kelvin. And then also my pressure needs to be converted to atmospheres because this is the R that I'm going to be using. So with the ideal gas law, you have to make sure that your units all match the units that are in the gas constant. So the conversion, if you can go back to one of our earlier slides, is 760 torr for every 1 atmosphere. When I do that, I find, keep this equation separate, that the pressure in atmospheres is 0.951 atmospheres, and my temperature, we'll do that math and plug it in down here. So N equals pressure, 0.951 atmospheres times volume, 2.025 liters, divided by this gas constant. Those gas constants will be given to you. You can see these are the 2 typical sets of units that we use for them. So 0.08206 liter atmospheres per mole Kelvin, and then times the temperature. When I added those together, the temperature ends up being 302.4 Kelvin. Look how the units cancel. Atmospheres cancel, liters cancel, Kelvin cancels, and I have 1 over moles, which means I'll end up with moles as my unit. And when I do that calculation, 0.0776 moles of O2. That is the number of moles of oxygen gas in the canister. This is a really low pressure for a canister. It's below atmospheric pressure. So it makes sense that I have an almost empty canister. If the pressure's so low, I shouldn't have hardly anything in it. If the pressure was higher, like maybe 10 times atmospheric pressure, then I'd expect to see more moles of oxygen here. So in the next problem, down you've got space to practice. Here you're given some grams of NH3. We want to calculate volume, and we have a temperature and a pressure. So grams, notice, is not in this equation. So you're going to need to first convert your grams to moles and then be able to work with our ideal gas law. So 2 sets of conditions, 1 set of conditions, but you're locked into these units, so you have to be extra careful.